Hello everyone, I'm Bo Wei, an assistant professor from Waseda University. The title of my presentation is Dash Live Video Streaming Control using actor-critic reinforcement learning method. This is a joint work with the University of Tokyo and the Waseda University. Here shows the overview of my presentation. Firstly, I will talk about the background about my research, and then I will introduce you the related work. After this, I explain the proposed method of this paper, and then I illustrate the simulation mechanism. Next, the experiment and the evaluation will be stated. Finally, I give you the conclusion and the future work. Now, I introduce the background. With the number of mobile devices increasing rapidly, large amount of network traffic has been generated. Among the total traffic, majority of the traffic is the video streaming. It is important to provide fair and high QoE video services for multi-user scenarios and in video streaming service. In order to guarantee high QoS and QoE, it is essential to control bitrate adaptively. Thus, the adaptive bitrate method should be developed. MPEG-Dash dynamic adaptive streaming over HTTP is studied worldwide as a unifying standard for video transmission. As shown in this figure, in Dash, the video is divided into multiple chunks, and each video chunk is encoded into different bitrate. User could select the proper bitrate adaptively to achieve the high-quality services. The algorithm for the bitrate selection is adaptive bitrate control method, ABR method. The ultimate goal of the adaptive bitrate method is to maximize the video bitrate while minimize the bitrate switch, rebuffering events, and duration at the same time. As shown in this figure, the higher throughput can meet the requirements of the user service. Well, when rebuffering happens, the user will feel annoying and may drop the video. This is not good to the revenue of the video provider. The main ABR methods can be classified into three categories: rate-based method, buffer-based method, and hybrid-based method. The rate-based methods select the bitrate based on the throughput condition, while the buffer-based methods decide the future bitrate with the buffering occupancy. The hybrid-based methods choose the proper bitrate based on the throughput and buffer condition together. In our former work, a TCP throughput prediction method in mobile networks called Trust was proposed. And as shown in this figure, in the former research, the communication data, including throughput, RSSI, time, location, and cell ID, are collected, and they are used for movement pattern identification. After it, the throughput prediction is conducted individually for each movement pattern, and then the predicted throughput will be utilized for smart mobile application control, such as the bitrate adaptation method. The former research has been published on the IEEE GlobalCom 2018. Besides the above research, a test-bed framework is constructed, which enables the evaluation of the Dash VOD streaming transmission over the diverse network structures in multi-user scenarios. The constructed network in this study is shown in this figure. The dumbbell topology is employed, and the Apache HTTP server is used as the content server in the root namespace. Two virtual switches, S1 and S2, are connected with each other, and the link between the two switches is bottlenecked to limit the network capacity for the content delivery. The properties of each link can also be modified accordingly. This research has been published on IEEE WCNC 2021. In this paper, reinforcement learning technique is utilized to develop a policy model to control the video streaming, as shown in this figure. When the live streaming is ongoing, the client will monitor the network conditions by a set of parameters, which are defined as states in the reinforcement learning model. The states include the throughput, buffer level, latency, skip time, rebuffering, and etc. During the streaming, the control model will generate an actor based on the current states, and then the bitrate packet buffer latency limit will be applied to the next segment, downloading. At the end, the total QoE will be utilized based on the state action reward datasets. The parameters of the policy model will be trained using actor-critic policy gradient method. The reinforcement learning model will be optimized repeatedly to improve the QoE. For the policy model, the three actions are independently built. The bitrate selection is modeled as discrete actions, where each action represents a bitrate level. And here, 4 bitrate levels are set. The target buffer is also modeled as discrete actions, which has two choices, 0.5 seconds or 1 second. The latency limit is modeled as continuous actions. Here, the latency limit can be selected within the range from 0 to 8. The state parameters are connected to the policy layer using linear combination. The general framework of the live streaming is shown in this figure. The live event is recorded by the video camera, and the raw video is transmitted to the transcoding server to generate the video contents at different levels. And then the contents are transmitted to the CDN servers to be accessed by the user. On the client side, the streaming application has an ABR engine to control the video streaming, and it will generate the decisions according to the current network condition. To simulate the live streaming mechanism, the simulator behaves in a frame-level way. In the simulator, the video information and the network trace information are necessary. During the simulation, each frame will be downloaded, and the time consumption will be calculated numerically using the network bandwidth and the size of the frame. And meanwhile, other logs such as client buffer size, rebuffering time, newest content, latency are calculated and updated. The QoE for the frame will be calculated and stored. At the end of the simulation, the QoE will be summed up to assess the streaming. In order to evaluate the performance of the control method, an evaluation standard is necessary. In the Multimedia Grant Challenge 2019, a QoE metric is provided, which includes the different factors. This metric is also adopted as shown in this function. This equation stands for the QoE reward of the nth frame, and it is calculated every time when one frame is downloaded. At the end of the streaming, all the QoE are summed up to generate a total QoE for the streaming session. In the equation, Qn is the bitrate, P-rebuffer is the rebuffering time, and T-delay is the latency. T-skip is the skipped time. W1 is the penalty coefficient of latency. It has two values. When the latency is larger than 1 second, W1 is set as 0.01. And when it is less than 1 second, W1 is set at 0.005. The live streaming simulation was carried out using 6 different network traces. The traces include the bandwidth logs at each second. These traces are obtained from an open dataset by the Mobile High-Speed Downlink Packet Access (HSDPA). The 6 network bandwidth logs were measured in the scenarios of bus, metro, tram, ferry, car, and train. 3 of the traces are shown in this figure, which demonstrate the dynamics of the network conditions. In the bus case, it can be observed that the bandwidth is almost under 2 Mbps before 200 seconds. Between 130 seconds and 200 seconds, the bandwidth is low, and after the 200 seconds, the bandwidth increases to about 5 Mbps. In the car case, the bandwidth is about 2 Mbps. In tram case, the bandwidth is relatively low compared with the other cases, which may only support video streaming with a lower quality. This figure shows the simulation results in all the scenarios. From it, we can obtain the total QoE performance of the live streaming in different conditions. It is found that the QoE in the tram case is the lowest. This is because the bandwidth in tram case is the smallest compared with the other conditions. Thus, the video quality selected in the tram case is always small. In this case, the total QoE in the tram case is the smallest, and the total QoE in the bus case shows the highest value, because the bandwidth of which is the highest after about 200 seconds. And the bandwidth before 130 seconds is not low. The total QoE of the car case is also high, as the bandwidth is always not low and fluctuate between the value from 0 to 4 Mbps. From the experimental results, we can conclude that the bandwidth is fluctuating differently in the various communication conditions. The ABR method control scheme plays differently in the various network conditions. And now, I give you the conclusion and the future work. In this paper, the ABR method was proposed to control the video streaming using the actor-critic reinforcement learning technique. And in this method, the historical streaming log, such as throughput, buffer size, rebuffering time, latency, are taken into consideration. And in this proposed method, the live streaming simulation is used to evaluate the proposal. Since the model needs training and the simulation can generate data much faster than in the real experiment. And the experiment results indicate that the QoE in the bus and the car scenarios show the best performance among all the scenarios. And the QoE of the tram case shows the lowest due to the fact that the low bandwidth. And in the future, more experiments will be conducted to evaluate the method. This means we would like to collect more data and more throughput traces in various scenarios, such as LTE and Wi-Fi, and then the method will be improved accordingly to achieve the higher QoE in all the scenarios and all the cases. And that's all the presentation. Thank you for your listening.